Hello. Last time, if you remember, we looked at square triangular numbers. That means triangular numbers that were square. Today I'm going to ask a slightly different question. What is a triangle double? Okay, so if you remember, the nth triangular number En is given by Tn is equal to half n plus 1. Okay, so now, we're looking for square triangles. So that's m squared is equal to Tn. More properly, and if you remember, we put n equal to x minus 1 over 2, and m is y over 2. Okay, that's where we were last time. That's going to be important later, so hopefully you can sort of remember some of this from last time. But if we go today, we're doubling triangles. I mean, we're looking for P and Q, and they're going to be natural numbers as well. So that the Heath triangle number is actually twice the Qth. So that means that half P plus 1 is equal to 2 lots of half Q plus 1. Now, based on what we did last time, it makes sense to do the same sort of thing again. So we're going to put P equal to x minus 1 over 2 and Q equal to y minus 1 over 2. Now, I'm just being deliberate because I want to establish a relationship between the square triangle numbers and the double triangle numbers. And the relationship is going to come out quite nicely through my choice of. So I've chosen my letters here with clever. They're not arbitrary. So if I do that, then what have we got? Well, we look trying to look at so half p. So it's just half p. So that's p plus 1 equals 2 times 2 times half q plus 1. So it means that half times x minus 1 over 2 times x minus 1 over 2 plus 1 equals a half, 2 lots of. I'm not going to cancel halves here yet because I think it's slightly, strange enough, it's slightly more transparent to leave it out. Okay, so there goes that, and that turns into x minus 1 over 2. That turns into x plus 1 over 2 equals 2 lots of y minus 1 over 2 times, sorry, there's a half missing, y plus 1 over 2. And then all kinds of things happen. I'm left with x squared minus 1 over 8 there. Difference 2 squares times is equal to twice y squared minus 1 over 8. And then what I've got to do is just a little bit of work. X squared minus 1 equals 2y squared minus 2, because I'm doubling. And then, well, here's the thing. 2y squared minus 1, minus x squared equals 1. We've got our second equation. Now look at that. That's quite nice because you know sort of seeing the relationship, aren't you? Because with the square triangles, we had x squared minus 2y squared equals 1. And with the double triangles, we've got 2y squared minus x squared equals 1. You see, there's a sort of they sort of are the same. The problem is, that difference is slightly problematic. Or what do I mean? Well, if you remember from last time, we tried looking at logarithmic numbers. So what you can do is you've got, if we had two solutions, A, B, and C, D solutions, and if I put A, B equal to lambda equal to A plus B root 2, and mu equal to C plus D root 2, then lambda mu, if you remember, is A plus AC plus 2BD plus AD plus BC root 2. These numbers satisfy AC plus 2BD. So, essentially, we can multiply this two solutions of this equation to give me two solutions of that equation to give me another one. The trouble is, it's when I go over here. So if I've got A prime, B prime, C prime, and D prime solutions with lambda equals A prime plus B, so lambda prime is A prime plus B prime root 2, and mu is equal to C prime plus D prime root 2. Well, lambda prime mu prime is the same thing as I'm going with primes. So it's AC plus 2. Same thing, but with primes. I've lost an A. Where's my A gone? Oh, as A there, wasn't it? A for D prime plus B prime C prime root 2. Well, the problem is that although these satisfy this equation, these satisfy that equation. And why is that? Well, it's actually related to the fact that this equation here is essentially, I've got a minus 1 there. And if you multiply minus 1 by minus 1, you get plus 1. So you can't multiply solutions of this equation and get another one. You can multiply solutions of this equation and get a solution of this equation by squaring it, essentially. Right. So what do we do? Well, actually, what we do is we say, well, look, there is a relationship. So there's a relationship between the two equations. So can we do a transformation? And the answer is yes, we can. And we can transform. We can transform between these and these. And how do we do it? We do it like this. The transformation looks like this. And there is an inverse transformation. Because it's nice and linear. Everything's all very linear, which is really quite wonderful. And perhaps I'll show you why a little later on. So that's the transformation. So I can go from one to the other, and you just prove this actually works. So we look at 2y squared minus x squared. Well, what's that? If that's equal to 1, then, well, that's the same thing as, let's get this right, 2 lots of x plus y squared minus x plus 2y squared. And then you do all the algebra, get all this x squared. This is where I usually mess things up because I go too fast. Moral of story when you're doing algebra, never go too fast. And if you look at that, well, what have I got? I've got 2x squared in the first bracket, 2x squared there, and x squared there. That gives me an x squared. In the second, this bracket, I've got 2 lots of 2xy, 4xy, minus the other 4xy. That one disappears. That's a big hooray. Then what have I got here? I've got 2y squared here, minus 4y squared. 2 minus 4 is minus 2, so I'm left with that. Now look at it. So you've basically got, for every solution of this, you have a solution of this. The two equations are related. And that means if you transform between these, it means we can transform between m's and n's and p's and q's. So I'm going to use the transformation there on my p's and q's. So remember that for my n and m were the square parallel number problem. So remember n was x over 2 and m was is y over 2. Now p, which is the double triangles problem, is that times 1 over 2, which, according to the transformation, was x plus 2y minus 1 over 2. And I'm going to write it like this. And then you see quite shockingly that this is n plus 2n. And now look, back we go. Look at this bit. There's that same form and same sort of thing with the q's. The q was y minus 1 over 2, which is equal to x plus y minus 1 over 2, which, if I bracket it out properly, is simply n plus n. It's a surprise. And so now what I've got here, I've basically got the idea that if I know a solution to the square triangles problem, I know the solution to the double triangles problem. So, what does that mean? If if we have two pairs of numbers, P and Q and N and M that are related like that, and that M squared is the nth triangular number, then you've got extension backwards as well. So let's just try a few now. Remember, we found 3 last time. We found 3 square triangular numbers last time. They were 1, 1, 8, 6, and 49, 35. Right, now we're going to find P and Q. Right, now P and Q. So what I do is I can do Q quite nicely just by adding things together. So Q, so for the first one, 1 plus 1 is 2. Add another M, that's 2 plus 1 is 3. Right, very nice. And just to prove, just check that. So the third triangular number is 6, and the second is 3. So it really is a double triangle, a double triangle problem. Yes, so 8 plus 6 is 14, and another M gives me 20. And the third one, 30, 35 plus 49 is 84, and another 35 gives me 119. And those are the first 3. This is quite fascinating, and there's a nice geometrical sort of reason why. If we can look at our geometry, well, okay, so what I'm going to do, I'm going to look at, essentially, I'm going to draw some axes. If you don't already know, the 2 equations that we've got, x squared minus 2y equals 1, and 2y squared minus x squared equals 1. These are 2 hyperbolae. And what's wonderful about these 2 hyperbolae is they have the same asymptotes. So what's asymptote? It's a line that the curve gets closer and closer to when it actually meets, except if you're an algebraic geometer, they meet at infinity. So these are the asymptotes, and the asymptotes are y equals x over root 2, y equals minus x over root 2. And then what I can do is I can now draw in, here is my, here is the hyperbole we get from drawing from square triangular numbers. And it looks like this. There are 2 naps to this hyperbola. There are 2 naps on a cone. And it's always good to have 2 naps. You wake up most refreshed. That's N-A-P-P-E, nap. And the other hyperbola, which is the hyperbola for the, let's do grey. The hyperbola for the doubling triangles, that looks like this. Like that. And you've got the other nap there. And they're all crossing at 1, 1, 1. And I think this is really wonderful. It means that the transformation that you've seen, where we transform between the capital X's and little x's, that's essentially form. It's not quite a reflection, it's a sort of reflection. Because it's swapping the grey hyperbola for the blue one. As a result, it means you can transform solution of one into the other. And it's because of a very, very nice property of the transformation. And you can really see the multiplication business. What would happen is if I try to multiply, if I multiply solutions in the blue curve, if I multiply solutions of blue curve, it will be on the blue curve. But if I multiply solutions on the grey curve, they will be something of the blue curve. That's what we saw earlier. I think that is really a nice geometric thing to do. So what you need to do, if you find a solution on the grey curve by multiplying, you actually need to cube. You actually need to multiply three solutions on the grey curve to keep it on the grey curve, whereas you only need to do two on the blue curve. So that's my little discussion on doubling triangles and how we relate them to square triangular numbers. I hope that that's been interesting for you. I hope if you're interested, I'll look at some other little problems of a similar sort or something else. Um, we'll see what happens. But I think looking at geometry of things is really quite revealing and actually understand situations a little better. Anyway, I hope you have a good day. I'll see you soon. Goodbye.